Then 6.3, local maximum and minimum. Knowing what local maximum and minimum mean. So local maximum and minimum, you can see if you make a graph. If you can't make a graph, we talked about like testing for it. And what that is, and so here they say use the change of sign of the first derivative. So that's where, let's say we have equals 7, f of 4 equals 0, f of 5 equals -2. Is the point 4 a maximum or minimum? That's what they're talking about here, using the change of sign. Now, we talked about this. So if you think about it, we have some graph, and 3, 4, 5. What's this graph doing at the point 4? Well, yeah, the slope is 0, which means wherever it is, that's like a stationary point. Now, at 3, it has a positive slope. So at 3, my graph has to be going positive. At 5, it says it's going negative. So is 4 maximum or minimum? Maximum. Because we can see that it was going up and then going back down. And actually, I mean, if basically at 5 there is some sort of negative slope to it.
Wait, so 0 is always a stationary point?
Now, that's a good question. Is 0 always a stationary point? That is y to the x to the third power. And if you take the derivative of that, you get 2x squared. If you put in 0, you get 0. Which tells you it's a stationary point. But is that a maximum or minimum point? And it's neither. So this is what we call a point of inflection. Right, through 2. So there's my function, there's its derivative. Now I'm going to use this change of sign test. I'm saying 3, -1 squared, 3, 0 squared, 3, 1 squared, -1 squared is, or sorry, -1 squared is 1 times 3. So I'm just going to now look at it. That's a positive answer. Then we have 0, and then 1 squared is times 3 is, yeah. So this is what tells me it's an inflection point. To the left of it, it's positive slope, 0 slope. To the right of it, positive slope again. And so if you kind of look at it, yeah, positive slope. Stop there for a second, and then was positive slope again. And that's what makes it this idea of an inflection. So, yeah, positive. There's your 0, and then positive again. And the same is true. It could be negative 0, negative, and it's still an inflection point. Okay? The graphical behavior of the functions, including the relation between those, optimization, and not required points of inflection where the second derivative is not defined. Is that what you were looking at, Nadine? What this means is when you do your second derivative and put the number in, being undefined is like you get a fraction dividing by 0. And so in that one case, you won't have a problem like that. That's basically what they're saying there. It'll be like the x cubed that I just gave you. That was defined at the inflection point, and so you would be expected to work with it. What is, now it says the graphical behavior, and actually one of the problems we're going to do is just this kind of problem, okay? But in your notes here, now optimization, let me jump here before I go back. What do they mean by optimization? Optimization is going to be something like finding an area or find a cost where it costs the least, costs the most, gives you the most area, gives you the least area. That's what optimization means here. And so you're obviously looking for a maximum or minimum value. There's f of x. Someone come and sketch f prime of x. So we have f prime of x, and we will have the second derivative of x. What would the first derivative of that curve look like? Now, it doesn't have to be a straight line. Tangents to curves are straight lines. And yes, we sometimes find the tangent, well, at a point. Yeah, I could ask you what's the tangent at that point, and I'm talking about a straight line. But I'm actually asking, yeah, and
Well, wouldn't it be like, if you're doing the rate of change, right?
mm-hmm.
Wouldn't it be like the line showing the rate of change, but like the dots go
Close,
like
sort of. Now let me follow along. This next graph, this first derivative, is supposed to be showing the rate of change based on where it is, x, y value. Okay? So where would I start? What is the slope at the maximum? 0. Meaning at this same x value, my derivative has a value of 0. The derivatives give you the slopes. And so at this point, the slope is 0. Now at this point, the slope is 0. So over here, it has to be 0. Now, to the left of 0, what's the slope of my graph? Describe.
Wait, what did you say?
The slope of, to the left of this point, the slope of the graph is one word, positive. The slopes are
Oh, yes.
positive, meaning then that my derivative graph has to be, and it doesn't have to be going up, it could literally just be going like this, or it could be going like that, but it's showing me that to the left of that point, my slope is positive. To the right of the point, it's negative until, when does it stop being negative?
After the minimum.
Yeah. It's going to be negative, 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 really negative, not so negative, till we get to there.
So it's like a general rule, if it's positive, the derivative will be negative.
Say again.
If the function's curve
Mhm.
has a positive slope, and then
So it has a positive slope here.
yeah,
Yeah.
so the derivative in that like region will be negative, like the slope of the derivative.
Yes, the slope of the derivative will be negative. No, I can't say. Oh, yes, I can. Yeah. But, so yeah, I'm going to, from here over, this is positive slope. So I need, oh no, I'm back in green. Sorry, bad call. I want this all to be blue. It's positive. Now, from this point down to the minimum, the graph is going negative. And if you think about it, yeah, this is kind of a roller coaster. You start off slow, then you get really steep and negative, and you start getting less negative again until you hit the bottom. So I should start off a little negative, get a lot negative, and then start coming back up, get a little negative, until I'm back to 0. No, think about what half of, these are positive values, these are negative values. You're positive if you're above the x-axis, you're negative if you're below. And so what I'm saying is, yeah, this slope right here is negative slope, but maybe a half. And so my graph should be at negative a half. Right here, you're going down and going down fast, which means I need to represent that I'm at a negative point and a big negative because I'm going down fast. And then, again, it starts to slow down until I get here. And then from this point, this direction, I'm back to having positive slope. So I'm back to the positive side of the x-axis, or the y-axis. Now, does that make sense?
So the slope is positive.
Your graph is positive,
but not the actual
not
slope.
the slope of the graph, no. I'm looking at what y values are these. These are positive y values, which tells me positive slope. These are negative y values, telling me negative slope. Back to positive y, so positive slope. So I have something, yeah, that I could say might look a bit like that. Now, I've got too much blue. Get my graph back. That's pretty close. So blue is the first derivative. Now, what's the graph of the second derivative going to look like? Where should you be looking to figure out where the second derivative is 0?
You look at the first derivative.
Right?
And because it's going like, oh wait. So first you see where it's going negative and then positive. So if that's going negative and that's going.
Where did I start with the first graph? What point did I find?
The maximum.
Yeah. I said, okay, I know something about this point, and I know something about that point, and I'll make that more.
Yeah, so the steepest point here would be the
Now, because what's the slope of that point? 0. So I knew 0. Slope of that point, 0. So I know that's 0.
So where
Now,
is the slope 0?
yeah, where's the slope 0 on the second, on the first derivative? The blue. Yeah. Right here.
Yeah, that's what I meant.
Oh, sorry. Right there, I know the slope is 0. Again, think about it. The first derivative is about slopes of the function. So the second derivative is about slopes of the first derivative. So there's 0 slope there. To the left of my 0, what's the slope? Negative. So this graph needs to be down here in the negative, and to the right of the point, the slope is positive, and so to the right, I need to have positive values. Now again, this is kind of my rough estimate sketch, and that's really all we're looking for. It could be, you could have it a bit curved, but for now I'm just going to give it that I know is definitely at 0, and this I just know are some positive slopes and some negative slopes.
So when you were saying that in a function it goes slowly and then really fast and then slowly and then it gets to the stationary point,
Yeah.
does that mean that for the y values it would hit a stationary point? The fastest point on that function would be
I don't. I'm going to say yes in most of the cases that we're talking about. Okay? But basically, it's hitting 0 at the fastest point, like in this area. So if the graph continued, there might be another spot where it's even faster. But yes, you can definitely say that between these 2 points, again, if this was a roller coaster or something, it was moving fastest because at that point, and it was actually going down at that point. But that's, yes, what you're saying is a right idea. Now, I want to flip back. I'm going to flip back to the page before. You have it right above. Finding maximum and minimums. They also mention use terms concave up and concave down. Concave up when the second derivative is positive. Concave down when the second derivative is negative. Now, you might need some arrows or something to connect, because we can look at our graph here. And I wish I could like cut it up into pieces. Now, this point right here, 0 and 0, what does that mean? And I know my graph's not drawing quite the way I want it for this. Let's see if I can fix it. What does it mean at that point? It means these three are all in a straight line. It's not stationary, because when I put a value into the first derivative, I'm not getting 0. I'm getting here. But here's what I want to illustrate this right here. The second derivative at this point, so going back to my original function, I'm asking, is this a maximum point or a minimum point? Well, I can skip the first derivative and go to the second derivative, because what it's saying is the second derivative, this point is negative, which means my graph is concave up. Yeah, now, here's what you can draw to help out here. Put here. Or sorry, concave down. I shouldn't have set up. Now, how to remember that? Look, a little smiley face. That's positive. Oh, look, a little frowny smile. That's negative. But here's where the logic goes wrong. A smiley face is a minimum value. A negative frowny face is a maximum value.
Yeah, but you can look at it as it makes a U.
Mm-hmm. That's true. But what I'm saying is, if you go back to, if I asked you, without seeing the graph, and now we have to pretend we don't see the graph. And I'm going to ask you, is this point a maximum or minimum? Okay? Now, well, if we didn't see the graph, and I just gave you a new equation, f of x equals 3x cubed plus 2x squared minus 1. If I gave you that, and here's your first derivative, here's your second derivative, and I said to you, at x equals 0, is that a maximum value or a minimum value? Now, looking at the first derivative, you put in 0, and then you put in -1, and then +1. and figure out is it positive, 0, negative, things like that. Or you can put 0 into the second function. This came out, so 0 plus 4 is positive. That's positive. The function is concave up, which means at x equals 0, no, it's a minimum because it's down there.
I got you.
Okay? And so that's what they mean by being able to use the second derivative as a test of is it a maximum or minimum. And basically the way they can simply check that is to say, here's the second derivative, not even give you the original function, and say x equals 3 is a stationary point, which again they're not telling you maximum or minimum, you just know stationary, and they ask you what is it, maximum or minimum. So you put the point they give you into the function, is it positive, is it negative, and then which of these two is it. All right, so this section here, yeah, there's kind of a lot going on with this. This, I think, is a kind of fun thing, to be honest, because basically I could have given you the second derivative to start and then said, okay, what's the first derivative look like? Okay, so what would the actual function look like? Just as a rough sketch, obviously, but we have a bit of an idea.
Wait, so minimum is concave up?
Yeah. So that's why I'm saying the logic, it was nice because positive is up, smiley, but when we relate it back to the actual function, it then means it's at the bottom.